Hello, 8th grade. We're going to continue our focus on scientific method. Let me just get my screen going here. Okay, so far we've talked about that scientists observe and ask questions. They often do research. They rely on their background information that they already have. They research experts in the field, maybe do some reading, look at some other experiments. There's a lot of different ways that scientists can observe. But typically we always start out with a question or a problem in science. And then the next step that we talked about was forming a hypothesis. And remember, a hypothesis is not just a prediction of your answer or your outcome. It's something that can be tested. So if it can't be tested, it's really not a good hypothesis. It's just a prediction. All right. So in our experiment, with the freaky frogs, we're going to continue to talk about scientific method. And the next portion of scientific method is how do we test that hypothesis? If it's a good hypothesis and it can be tested, then how do we go about that? All right, so the next step in scientific method is to design and conduct an experiment that will test your hypothesis. Now remember, in the freaky frog problem or situation, they had 3 different hypotheses, and they focused on one, and that was the exposure to UV light and its effect on frogs' deformities or not. So that's the one we're going to use. I want to review really quickly about independent variable, dependent variable, and controlled variables. Remember, in a good experiment, you only have one independent variable. You only change one factor to see how that affects the outcome of your experiment. So there can be only one, right? Okay, and then your dependent variable is the observation or the measurements that you take of the outcome. In this case, our outcome is going to be the frog deformities. So the hypothesis that we're focusing on in practicing the rest of scientific method is that if an increase in exposure to UV light is causing the deformities, then frog eggs exposed to UV light in a lab will develop into deformed frogs. Now that's really long, and you can actually make it a little bit more simple, especially if that is your hypothesis and you're definitely saying that it's the UV light that's causing the problem. There's a shorter, sweeter way to say it. Okay, you could say if frog eggs are exposed to UV light, then they will develop into deformed frogs. Now I want to make a little bit of a side note here, because you know, every frog that I know of that grows in nature is exposed to UV light. Anytime you're out in the sun, you're exposed to UV light. That's why your mom always tells you to put sunscreen on when you're going to be outside for extended periods of time, because she doesn't want you to get sunburned, right? So there's always exposure to UV light anytime you're outside. So this experiment is a little off, but we're going to go with it because it's a pretty good example for understanding the steps of scientific method. Okay, so our hypothesis that we're going to design an experiment around is that if frog eggs are exposed to UV light, then they will develop deformities. When they develop into frogs, they will be deformed. All right, so I want you to notice here on the controlled experiment, let me do this a little bit. Oops, sorry. All right, so a controlled experiment here is an experiment that tests only one factor at a time by using a comparison of a control group with an experimental group. Now, the control group, to me, really should be just frogs in nature and however much they're exposed to. But in this experiment, what they did was they didn't expose the frog eggs to UV light at all in the control group. All right, so our independent variable in this experiment is exposure, the amount of exposure to UV light, whether they're exposed or not, or how much they're exposed. And then our dependent variable is going to be if we have deformities or not. Now, in a good experiment, remember, we have to control all the other variables or all the other factors that might affect the outcome. So if you'll look at this table that they have here, This will give you an idea of the three groups. Okay, so they have control group 1, and that's 0 exposure to UV light. And then if you notice that the kind of frog eggs that they're using are the same. They're using leopard frog eggs for all three setups. They're using the same number of eggs, and then the temperature of the water is the same. Okay, so those are their controlled variables. These are other factors that might possibly affect the outcome of the experiment. In other words, it might cause deformities or not cause deformities. All right, so they have three groups that they have set up. Each of them are leopard frog eggs. Each of them has 100 of those frog eggs. The temperature of the water is maintained. The only thing that changes is the amount of exposure to UV light. Now, this will be our independent variable then. Okay, so let's look at the setup here and make sure that they controlled all of their variables. Here's your control group, no UV light exposure. You notice there's no light at all here. They have the same type of frog eggs and the same number, and there's not 100 little circles, but trust me, they're the same. Okay, so group 1 is our control group, no exposure to UV light. This one, if you notice, they're going to expose these frog eggs for 15 days. 15 days. And then this group, group 3, was exposed for 24 days. Quite a long time. All right. So that's a pretty good experimental design they've set up. So you've got one independent variable. You're waiting to get your results, which we're going to look at in a second, and they've controlled any other factor that may cause deformities in frogs or may cause a change in the outcome. Right? All right, so they actually have their information here, their data or their information. So the group 1, the control group that had no exposure to UV light, they ended up with 0 deformed frogs, no freaky frogs in that bunch. Okay, and then in group 2, those that were exposed for 15 days, no freaky frogs. So good so far, right? And then group 3, those eggs were exposed for 24 days. Well, look here, they ended up with 47 freaky frogs. That's quite a lot. So 47 out of 100, right? They started out with 100 eggs. Now, you know that some of those eggs are not going to actually develop into frogs. They're going to die before they reach adulthood. But that's a pretty substantial number out of 100. Okay, so as part of first, you've planned the experiment, you've designed the experiments, and then you conduct the experiment, which is a fancy way of saying do the experiment or run the experiment. Okay, and once you've done that, the reason you're doing all this is to collect data to either support or not support your hypothesis, right? So collecting data is a very important part of conducting an experiment. So if you look here, they collected that, and the data, they knew that there were, sorry. All right, so this is their data. 0 deformed frogs, 0 deformed frogs, and 47 deformed frogs. Okay, so what they did was then they put that into a graph like this, a bar graph. And typically when scientists have a large group of data, a large amount of data, they like to put it in some type of visual representation, and most often that is a bar graph, a line graph, or a circle graph. So in this case they used a bar graph because we typically use bar graphs in science when we're comparing pieces of data. So in this case they wanted to compare the groups, the number of deformed frogs per group, and it's very clear to see from this visual representation, the bar graph, that those that were exposed to 24 days of UV light have a substantial number of deformities as compared to the other two groups. In fact, the other two groups had none. Okay, so it's very important to collect data. It's very important to organize that data, and then it's really great when you can to make a visual representation of it. Okay, then the next step of scientific method, moving on, is that you are to analyze those results. In this case, the word analyze just means to make sense of it. What does it all mean? Okay, I have this data, I have this information, I ran this great experiment, I designed this great experiment, I had this wonderful hypothesis, and so now what does the data tell me? What does all the data mean? Okay, so in this case, you could definitely say that your hypothesis was supported. And if we go back to the hypothesis, it says if frog eggs are exposed to UV light, then they will develop into deformed frogs. Well, in this case, the ones that were exposed to a large number of days, 24 days, definitely developed a lot of deformities. So you could say that your hypothesis was supported. So we know that that's what that data means, is that yes, UV light exposure can cause deformities in frogs. Now, when you go to the next step, which is draw conclusions, this is where it gets a little bit tricky. Okay, you have to include, first of all, you have to restate your hypothesis. So, I said that if frog eggs were exposed to UV light, then they would develop into deformed frogs. That was my original hypothesis. And the data, which I analyzed, seems to support that hypothesis, okay? But that you only tested one variable. You only tested one factor. So you cannot say definitively without any doubt that UV light is the only reason why those frogs in Minnesota were all deformed, okay? If you go back and you do another hypothesis, for example, with chemical pollutants, you might end up with similar results. You might have 47 out of 100 of your frogs that have developed deformities. So then what do we know? Then we know that UV light exposure can cause deformities, but also chemical pollutants can cause deformities. So when you're drawing conclusions about your experiment, you have to focus on your hypothesis and all that you know for sure, beyond a shadow of a doubt. You know that UV light exposure, especially extreme UV light exposure, can cause deformities, but you don't know that that's the only cause because you only tested one variable. Okay, so in your conclusion statement, you're going to restate your hypothesis. You're going to say whether the data supported that hypothesis or not. Then you're going to explain maybe what you did wrong, maybe you didn't control all the variables. And then the next part of drawing conclusions is saying, what next? How could I extend this? So based on the data that we collected from this experiment, you could definitely say that your hypothesis was supported and that UV light exposure can cause deformities in frogs. But you might say, now I want to go on and test the hypothesis about chemical pollutants in the water. Maybe they have some effect on frog deformities. So that's a conclusion statement. In the template that I have on Moodle, it will explain, it'll very clearly state the statements that need to be in your conclusion piece. And we will practice that as well. Okay, now then the last part of scientific method is communicating your results. And I know we're just 8th graders, we're just doing some experiments and playing around with scientific method. But you need to get in the habit of communicating your results in some way. Scientists who are, part of our global community, scientific community, they are often publishing their work in different journals and magazines and things like that. It's very important to get your data out there, especially if you've done some really good experimental research. For one thing, you don't want people repeating what you're doing. You don't want people to waste time, but you also want some review by your peers. So you want other scientists to be able to follow your procedure to test that hypothesis and get the same results. So if I copy this experiment with the frog eggs and UV light exposure, I should get about the same results if it is an accurate, good experiment, good research. Okay, so that's one reason. And also, you don't want to keep any good information or even bad information to yourself. We need to know what's going on in research so that we don't repeat ourselves, but also so that we're aware of what's going on. And let's say you're doing cancer research and you find something that that might lead to a cure for a certain type of cancer. You don't want to keep that to yourself. You want to share that with the larger population, so also you can have peer review, you can have other scientists checking your work, and maybe someone will think of a great idea to extend that, and we can move forward if we all communicate and are, in it together, if you will. All right, so the last step is communicating your results. So in my class, that will involve, writing a lab report, maybe doing some type of presentation to the class, or, posting something on your blog, but you will have a little practice with that. All right, so that is that's the rest of our scientific method study, and I hope you've learned a lot. We will continue working on different examples and using different scenarios in class. So I hope this was helpful, and I'll see you in class.